given the allocation that I do. And then we have a neural network constraint that basically takes as input all the average clock per instruction of my, so the features related to my decisions, and produces a set of a vector of temperature or a temperature for every single core. And then, for example, I want to minimize the maximum temperature that the core achieves. So this is basically a work that has been described into a AAAI paper. And the thing that is nice is that you can also, if you have a thermal controller there, you can also learn the thermal controller behavior. So you learn how to avoid the thermal controller to slow down your platform. And basically, you are really considering the temperature in your decisions. And this is for neural networks. So there are also other machine learning models that can be inserted into a combinatorial optimization model, like decision trees, for example. And this is easier, way easier. Or random forest. You can really do a lot of things. But let's consider a decision tree. So decision tree, everybody knows what it is here in this audience. But basically, you have features that are related to our decisions. And basically, in each feature, you have a test. And in the leaves of this tree, you have the classes that you want to predict. Or we can have regression trees, where in the trees we don't have classes, but we have numbers, basically. And the thing that we can do, so how can we embed a decision tree in constraint programming? Well, we can have a decision variable for each attribute that is related, for example, to our decisions. And we have a decision variable for the class. So I have to create a global constraint that relates the input, which are related to our decision, to the output. And we want to enforce consistency on this constraint. And this is the tricky part. Why that? Because, of course, you can always see that a path is an implication. It's so easy to insert an implication into a constraint programming model. But the problem is that basically, okay, so a tree defines all the paths, and basically we can say that y, the class, is equal to 1 if, and then the description of all the paths. A is greater than 20, and C is equal to 0, and B is greater than 20. And you can really put these implications into the model directly. So the problem is that it's a polynomial size encoding, polynomial timed propagation, but it does not enforce generalized R consistency on this constraint. So basically, we do not achieve the maximum filtering that we can achieve with this constraint. So we can do better, definitely. So for example, we can use a table constraint. The table constraint is that we can, in a way, discretize our attributes, and we create a table with all the paths, and we use a table constraint that is a global constraint that is present in almost all constraint programming solvers, and we can propagate the constraint. I mean, we have to work a little bit because continuous attributes should be discretized using thresholds appearing in the tree and so on. But we have done a lot of experiments. We have now a technical report that is almost ready because we have tried a number of different encodings of these decision trees, like we have used multiple decision diagrams, compressed tuples, negated normal forms, decomposition approaches. We have really done a lot of attempts for inserting this decision tree in an effective way, in an efficient way, to try to achieve the maximum possible filtering into constraint program. So let's see some results. So the question is, does the insertion of a machine learning model into a combinatorial model pays off? And of course, we have to compare this with an expert design model. And we have, we have used an expert design model that basically tries to perform load balancing in the application of workload dispatching. So the intuition is, if I try to balance the load, well, the temperature can be, kept down. At least can be limited. But the problem, and on the left side, we have results using an expert design model that uses basically load balancing heuristics. So the problem here is that you can see, so the redder, the hotter is the core. So basically we have these instances that are describe our architecture, and the solution of load balancing using the load balancing designed by the expert. This is a MIP model and an expert design model. So we can see that in general, I mean, it works pretty well, but here we have, as you can see, hotspots that are not really good for the platform. For example, in this instance number 9, instance number 3, we have some, in the first one, we have really hotspots. So we now have used an empirical model learning approach that learns from data the thermal behavior of each core. So does it pay off? Yes, it does, because if you see, I mean, just just by looking at the description, I mean, of the temperature here, we can see we don't have the hotspots that we had here, and in general, the temperature is kept much, much lower. So the thing is that clearly an expert cannot really be aware of all the different behavior of different cores, for example, because there are a number of aspects that come into play when we want to describe a thermal model, like the position in the core of the core on the platform, for example, the how close or how far is from the cooling part of the platform, and so on. So if you instead, if you learn from data, you understand and you learn these, how can I say, these different behavior by exploiting data, and it is of course it pays off. Okay, so I mean, this is basically another way to say that. So some points that should be discussed. It's really, I mean, empirical model learning in a way enables combinatorial optimization to be applied on systems where, for example, in general, combinatorial optimization is not applied, like, for example, on traffic, on incentive design, and so on. When you have to deal with a complex dynamics, or also on system where you have a model, but the model is too computationally expensive for being introduced into a combinatorial model. So constraint programming, of course, is very well suited to host machine learning models, because constraint programming has this tool of having global constraints that are basically software components describing a part of your problem that embed a filtering algorithm that enables you to prune the search space. So it's very easy to embed a machine learning model as a global constraint, but we have the fact that the machine learning model is just a constraint. So you can use, together with this machine learning model, many other side constraints that help reducing the search space. So it's very flexible. Of course, we have to address a number of issues here to make it work. So the first one is that you can always embed machine learning in local search. So the thing is that, can CP work better? And the answer is yes. Yes, why that? Because we have propagation. So if we use machine learning to propagate, then we can really reduce the search space we can really reduce the search space thanks to the propagation of the machine learning model. Clearly, we have to balance, basically as usual, we have to balance the inference. So the inference that we perform in every node, and also the inference that the machine learning component performs, should be effective but efficient. So, for example, embedding a shallow network is a piece of cake, but embedding a deep network is really, really difficult, because it takes a huge amount of time, but it does not propagate that much. So I will come back to this very shortly. So inference should be efficient. So we have to really find a way to embed a machine learning model into combinatorial optimization in a way that is efficient to propagate and effective, so produces a good propagation, tight bounds to our variables. So we have, I mean, that complex learning, machine learning model are more accurate, but are very slow and can provide a weak propagation. While, for example, sometimes simple machine learning models, even if they are less accurate, they could provide effective propagation. So we might have apparently good solutions also using a low, less accurate machine learning model. But there is an accuracy optimization trade-off that we have to take into account, how to characterize it, how can we find design rules. So there is now a work that we are trying to do through a Google grant that we had, that is how to encapsulate a deep network into a constraint. And the problem here is that the deep network can be very, very accurate, of course, in predicting a given observable, given our decisions. But the problem is that since the network is very deep and the gradient vanishes, also the propagation vanishes. So if you tie the bounds of the output variable, nothing happens on your input variable. At least, I mean, using traditional propagation method and using the propagation method that I showed you before for the shallow neural network. So the thing that we have to do is to define propagation algorithms that produce a reduction in your search space, and you have to be efficient. So we have basically up to now being able to insert into a constraint up to 5 layers of a neural network, but not more than that, because otherwise the propagation vanishes. So we are really working on that. But so if you have any suggestion, we are very happy to listen to. Second problem is the fact that not always the most accurate models are the best for your optimization, for being embedded into an optimization model. And now I explain you why. So let's try to consider this. We have a training set and we have a really good machine learning model that approximates this point in your data set. But you know what? I mean, suppose that we want to optimize this function. Where we work is here, okay? And now suppose that we want to, of course, work here. This is the input configuration, output values, predictions, and this is the final solution, okay? The final solution because we want to optimize, for example, this function. So this is a very accurate model almost everywhere, but here suppose that the true value is there, and it was not a value in our configuration. So the problem is that we are really underestimating this true value, and the problem is that in optimization, we do not really sample the training space in an uniform way. So we want to concentrate on those parts of the search space that are optimal for our objective function. So we have to be accurate there and not, in every, okay? and not everywhere in our sample space. So our model, to be effective, should be accurate where the optimization goes. So the thing is that we can use active learning. So we can, in a way, refine the machine learning model around the part of the space that is interesting for our optimization algorithm. Because we really want to go into part of the search space that are optimal for our objective function. So we can, of course, borrow concepts from black box optimization, surrogate model construction, but basically we have to try to sample, more deeply and more effectively and more frequently the part of the space that is interesting for our objective function. And we can also be less accurate on the other parts of the search space. So this is something that should be very taken into account. Another issue, machine learning models provide kind of confidence levels. So they provide us, a kind of uncertainty on the prediction. So can we take it into account while optimizing? And of course, yes, you can do that because we have a number of optimization models that take into account uncertainty. So we can, for example, embed machine learning models into stochastic optimization solvers that take into account the uncertainty that you have on the input, the uncertainty that you have on the output, and optimize for that. And also, you know what? Some errors are more important than others, of course. And for example, in the temperature example, in the thermal aware workload dispatching example, if I underestimate if I overestimate the temperature of a core, well, of course, this is not good, but I can survive with it. Why that? Because I would not, basically, I would not explore some solutions that would be otherwise feasible, okay? So if I overestimate. But if I underestimate the temperature, then, of course, I can run the risk of overheating, because my workload dispatching thinks that the temperature can be 60 degrees while instead it's 75. So underestimating is really worse than overestimating here, and we can take this into account by, for example, changing the loss function of the network, but also in the stochastic optimization component in the solver, by balancing the errors and weighting the errors in a different way. So there are some extensions that we have done, and we are working on. Sorry, we're not yet done, but we are working on. And basically, these extensions are the following. So we want to exploit empirical model learning into two different directions. One is hierarchical optimization. So what it means is that in many optimization problems, the problem is so large that we cannot really have a single model for modeling everything. So, for example, suppose that we want to optimize, an energy balancing on a number of different power plants, virtual power plants, and we cannot really know the details of each of them. So every single place optimized by their own, but we want to optimize overall. So the thing that we can do is to learn how a single optimizer works by creating a training set of feasible solutions for this low-level optimizer, and then cast the learned model into a higher-level optimizer that basically provides higher-level strategies. Because having a unique model of the overall system can be infeasible, can be non-practical, non-computationally affordable. So we can use basically empirical model learning for learning the behavior of optimizers, of optimization components, and then cast these components into a higher level model. And also for offline-online optimization. So in offline-online optimization, you have some decisions that are taken offline that are, say, for example, strategic decisions. But then online, you have to refine them when you have that, for example, the uncertainty is revealed. And the nice thing is that, in general, the online algorithm is a heuristic algorithm, not very smart in general, because it should be fast. It's not really anticipatory, for example, so does not take into account the uncertainty, and it just reacts to events. And the thing here is that if the offline part is aware of the fact that the online algorithm comes after that, then it might take decisions and might guide this online algorithm toward the promising solutions. And for doing that, the offline solver can learn the behavior of the online one. And we can basically learn the behavior of the online solver, cast it into the offline solver, and use the offline solver can be more effective for dealing with the overall problem. Well, I'm done. Basically, there is all these material is on GitHub. There is this repository mlopt.github.io. And we have the description of the method. We have many application examples. One is really nice because it's on zombies that are infecting our world. And basically, it's really nice how we can predict how these zombies will infect people, and then try to understand which are the actions that can be taken for avoiding this. So it's a running example. There are many resources like papers. There is a running survey that we have published at HCAI last year, and it's updated regularly. We have some MMlib embedding techniques. for pre and post-processing methods. There are some readers for popular machine learning libraries and the tutorial. So basically, if you want to try, we are, of course, available for providing support and help and for collaborating. So thank you very much. In time, right? Yes, almost.
Okay, so thanks for the talk, very perfect in time. So, questions?
Yeah. The propagation problem. Absolutely. Yeah, okay, good. Thank you very much. I didn't know that. So if you can send me the reference, it would be very interesting. Yeah, Fede. Absolutely. I mean, the important thing is that you need to have a way to embedding I mean, the machine learning model into a combinatorial one with an effective propagation technique. Otherwise, I mean, it's not useful. But in case you have, of course, this could be a workaround. Yeah. Yeah, this is a very good question indeed. I mean, when you have these kind of domains, then you have to resort to simulation. There's no way. I mean, the first thing that you have to have an accurate simulator, which is not easy for mobility. I mean, because in general, even micro simulators are. We have tried this into a project. The European project was called Colombo, and we collaborated with DLR. DLR is the German Aerospace Center, and they have micro simulator that is called Sumo. That is probably realistic for the German traffic, not for the Italian one, for sure. But yeah, I mean, if you have a realistic simulator, then you can try to create a training set using that. But yeah, this is definitely a problem where you, or real systems. I mean, if you want to try many configurations, it's like for reinforcement learning, you have to have the possibility of making errors, for example, of trying configurations that are not good. So in general, for example, with the thermal dynamics of the platform, we had the real platform, and we could, run many different software workload dispatching. But the problem, the fact was that basically on the platform we had a thermal controller, so we couldn't. Our training set was biased by the fact that we had a thermal controller. So we don't want the thermal controller to start so in this case we had the real system to run our example. But in general, in traffic, for example, you have to resort to a simulator, absolutely. But even for incentives, you can resort to past data, for example. But you don't really have, so you can resort to studying past data and past incentives that have been given. But I mean, the capability of forecasting the new incentives is something that is, of course, quite difficult. But still, I mean, it's better than nothing.
Time for more questions.
Exactly. Yeah, this is a really good question. So this is basically the difference between control and optimization. So the thing is that this is done in the controller. In general, for combinatorial models, we try to, the combinatorial model that I was mentioning is an offline combinatorial component. So basically you take the decision and then you make it run. Then what you are suggesting is instead an online optimizer or a controller that in a way, also observes the dynamic, observes the temporal dynamic of the system, observes the thermal dynamic of the system, and takes decisions, right? Because you are right, the system can change, in fact. Yeah, but this is there is a substantial difference between, what you are saying that is what is done, for example, in system identification. So they are, in a way, learning the relation between the input and the output of the system, but in a dynamic way. So they are taking decision with a very limited temporal time horizon, okay, and they have to take decisions while the system is working. Here, this is an offline, but yeah, definitely this can be used also in this setting. Very, very, very interesting question.
So let's thank Michael again.
Thank you very much for listening.